Welcome back. We are looking at the code for Tikhonov regularization as well as Levenberg-Marquardt regularization or Levenberg-Marquardt for Gauss-Newton in this video. As we had discussed in the class, the basic idea of both Tikhonov as well as Levenberg-Marquardt is to modify the basic Gauss-Newton algorithm so as to make it a little bit more stable. Now, the example that I have chosen here, because we did this example in Gauss-Newton, is optimized not for showing the good properties of Tikhonov and Levenberg-Marquardt, even though I will show a little bit of it. Some of it should be visible, but it is optimized so as to enable you to do this by hand. I am, of course, showing this by code because showing this by hand in a video recorded lecture actually looks quite boring. You can do that by hand also and cross-verify with the code, which will be uploaded for people taking this course for credit. We are going to repeat the same unsteady inverse problem that we did the last time. Remember, we had a first order system which had some heat generation within it, and of course it was losing heat via convection, and we had collected temperatures at various time points, like 10 seconds the temperature is 3.1, or the temperature deficit is 3.1, T minus T infinity, and so on and so forth. And we already knew that the forward model had the form theta equal to A times 1 minus E to the power minus BT. As I had mentioned in the overfitting lectures in this week, we actually need a lot of parameters to require the need for regularization. Either I need to add a lot of noise. I have not chosen to do that. But if we look at this problem, the primary purpose of showing you this course is how small a modification you need to make to the Gauss-Newton algorithm in order to get Tikhonov regularization as well as Levenberg-Marquardt. So we are going to continue the same problem. I'll show you what happens when you don't add damping of the form of Tikhonov or Levenberg-Marquardt, and then what happens when you add those and how the iterations proceed. So remember, I have just done the same thing as the last time, encoded the data or basically stored the input data. This is just the tabular data which was there, T and theta. I changed the names of the variables just for convenience. I called X as T. You can see it's the same as the time variable. And Y is the theta variable. Again, just for notational convenience. M, of course, is the number of data points, which in this case is 6. Okay. So last time, we had started with an initial guess of 35 and 0.004. I just want to show the same initial guess. I'll change the code. We will ensure that we are getting the same results for lambda equal to 0, and then we will start changing lambda. Okay. The model remains the same because the forward model has not changed. So y hat still remains 1 times 1 minus e to the power minus bx in this case. X is basically just time. Then dy dt or dy dA is the same as last time, 1 minus e to the power minus bx, and dy dB is also the same as last time. Okay. Now here is where we are actually going to do the iterations of Tikhonov. Okay, so we are going to do iterations of Tikhonov here. Again, same as before, you first find out what the forward model is. We can in fact write that after finding the forward prediction. So remember, we first make the forward prediction, take a guess for A and B, which we have done here. Here are the guesses. Take a guess for A and B. For that A and B, for every X in your data set, find out the Y. Okay, so we did that. So once you do that, you can also find out the gradients. So the Jacobians we calculate, same as Gauss-Newton, which you should remember from last week. Del Y del A or del Y hat del A and del Y hat del B, which we have already stored here. Then we create this matrix Z, which is what lets us solve the Newton system. The derivation was there last time. I also showed you not really a derivation, but a semi-derivation for Tikhonov and Levenberg-Marquardt this week. So here is the Newton system, Z transpose Z times delta A equal to Z transpose D, where D is the error or the difference between what your prediction is and what the actual value of Y is at those points. Okay, so for example, prediction will be theta at, actual value is whatever is there on this column. That's that matrix D here. Okay. For Tikhonov, it almost stays the same, but you can see that for Tikhonov, you have a small variation. You have this additional term lambda I, on the left hand side. What it does, as I told you in the class, was it makes the equations or the linear system of equations a little bit more diagonally heavy, which stabilizes the system. Okay, so it is like adding a small term in the denominator. If you have some a by b term, instead of that, if you do a by b plus lambda, that makes it a little bit more stable. Okay, so the code here is simple. Before I added this lambda term, it just looked like dA is LHS by RHS, where LHS was Z transpose Z. Now I have added this term. I here simply is the identity matrix. I'll show it to you when I run it. So this is simply the identity matrix. So lambda times I, lambda we have given the older value was 0.01, but I have given a value of 0 now. When you run it, you will see what happens. Okay. And then of course RHS, the same thing. Okay, you are basically doing inverse of LHS multiplied by RHS using Gauss elimination. This is the MATLAB notation for that. And then you update your A, update your B. Really nothing much has changed from Gauss-Newton. As you can see, it's a trivial sort of small improvement over Gauss-Newton, but it helps stabilize things, which is why it is very popular. Well, not really just Tikhonov, as I will show you, Levenberg-Marquardt is a little bit more popular. So we can go ahead with the same parameters as before and see if we obtain the same results if we set lambda equal to 0. And you can see, please remember these final values, 48.8239 and 0.0070. So if you wish, we can just add these final expected values for Gauss-Newton are A equal to 48.8239 and B equal to 0.0070. Okay, so these are the ideal values that you get, and we got here, if you notice, 1, 2, 3, 4, 5, about in 5 iterations. Okay, so about 5 iterations. If you wish, we can add the iteration number also, so just so that it is a little bit clear. I'll run it once more. So you can see at around the 5th iteration, we attain the value 48.8239 and 0.0070. Now, what we are going to do is play with a few values of lambda. As I said, really speaking, you can't expect too much of an improvement here. And in fact, as I told you in the theory class, it can damp things when they are already working well. Okay, so you are sort of trying to remove off too much noise from the convergence process. So it can actually do a little bit worse. So let's see. We will have to play with it. Instead of taking lambda equal to 0, let's say we take lambda equal to 10 power minus 4, or let's say 10 power minus 7, which is really small, and we can run it. So you can see that it has still converged in about 5 iterations. Okay, so the convergence process is slightly different, but lambda equal to 10 power minus 7, which is very small, close to 0, still gets you about 5 iterations. If I make lambda very large, let's say I make lambda 1, you can see it has not yet converged. It has actually damped things. It's pulled them down and it's still converging. It doesn't converge. So somewhere in between, you can try lambda equal to 10 power minus 2, for example. So for 10 power minus 2, you have the 6th iteration. So we can try something like 10 power minus 3. So here you see maybe once again the 5th iteration. Now, the important thing here is to see what all these terms are. The left-hand side is a 2 by 2 matrix. So notice, as I had told you before, Z transpose Z is a square matrix. You should remember this from your Gauss-Newton algorithm class also. But this is, you can notice LHS is a 2 by 2 matrix. The identity matrix, as you can see, is just a 2 cross 2 matrix of size 1. The new LHS with which you solve will be just that plus lambda times I. Okay, and the RHS is as it has to be. It's a 2 cross 1 matrix. So that's what happens here as we go forward. Okay, so we can try one more lambda value, but more than that, I want to change the initial guesses and let's see what the effects are. So suppose I change the initial guess, and once again, just to set a baseline, I put a lambda of 0. Now you can see that when you put a lambda of 0, this doesn't converge at all. Actually, let me give a little bit gentler as an initial condition. Okay, so when you put a farther away initial condition and you try to converge it, it gets to around 7 iterations, or actually if you come to a 0.8239 at about 9 iterations. Okay, so 9 iterations is what it takes for the new initial condition. Okay, so this is just to remind ourselves that it's 9 iterations for the new initial condition. And now we can try with various values of lambda. So let's say I take lambda as 10 power minus 4. You take around 8. Okay, so as I said, you can't expect much improvement with this kind of Tikhonov, but just to satisfy ourselves, we can try a few other values. So this gets in 6. So you see, you get a slight advantage with Tikhonov with a particular lambda. So the lambda, as I told you in class, is called a hyperparameter, much like alpha, the learning rate in gradient descent. These are not parameters we are solving for. A and B are the parameters we are solving for, but you get some advantage for slightly differing lambdas. Some smoothing can be expected. In this case, again, if we increase lambda too much, it took too much time, right? I mean, it's not converging exactly to that value. Within 10 iterations, it could probably take more. Of course, all these iterations are a little bit painful to do when you do them by hand. Nonetheless, again, people doing it for credit, I would recommend that they do that. Okay, so somewhere between 6 and 8 iterations is what Tikhonov takes. Okay, so we saw one case with some slight advantage. This was lambda equal to 10 power minus 2. But otherwise, at least for the original initial conditions, there was practically no advantage. You really have to look at a combination of, when the number of parameters is large, you'll actually find that Tikhonov works better than pure Gauss-Newton for several cases, especially when your initial guesses, which typically will be the case, will be far off from the actual values. So what I want to do is now just switch from Tikhonov to Levenberg-Marquardt, which I will show you in the next code. So let's see that. So here you see the Levenberg-Marquardt code. Again, practically identical to the Tikhonov code, which we saw earlier. You can see I have practically made no change here, except there will be a small change below. So, but just to walk you through this, the same initial model, the same data, and the same initial guesses. So I have, commented out the new guesses that we made the last time. And again, I have set lambda equal to 0. This is generally a good programming practice just to ensure that you're getting the right values, at least for the same old cases. And same model, same gradient, and same initial thing of calculating the model and then proceeding further. But the usual Gauss-Newton step was, as we saw, Z transpose Z delta A at equal to Z transpose D. And the Tikhonov was that plus a lambda I. And the only change we make in Levenberg-Marquardt, as I told you in the class, was have effectively a variable lambda for each variable. Another way of doing it is lambda times diagonal of Z transpose Z. So this is the term that you have to be careful about. So here notice Z transpose Z, this is Z transpose Z plus lambda times this matrix DL, which is the diagonal of LHS. I will show that to you shortly as we run through the program. And then the rest of it is exactly the same as before. So programming wise, it's extremely straightforward. In fact, even calculation wise, it's not particularly harder than Tikhonov or original Gauss-Newton. It's the Gauss-Newton which is a hard part in these problems. So what we will do is let's just start running the program. So when we come here, please notice what Z is. Z is actually, you can see 2 columns are there. The first column is del y hat del A. It tells you how much your prediction would change if you change A. And the second column is del y hat del B. It tells you how much the prediction would change if you change B. Obviously, our job is to change A and B and figure out what is the optimal sort of place where we can move this y hat to, or a and b to. Okay, so once we have that, we first can calculate this z transpose z term. Okay, so if we calculate z transpose z, let me just do that. If you calculate z transpose z, it comes to some term, but then you calculate the diagonal. Okay, so the diagonal is exactly the diagonal terms, but I have written it as a full matrix just so that you can add these two matrices here, multiply that by lambda, z transpose z plus lambda times this diagonal term becomes the new LHS, and then we solve the z transpose d, which is again an RHS term, and we do that repeatedly. Okay, so let me just run this, and once again let me actually put a iteration number also here. Okay, so the same as what we saw last time, in about 5 iterations, we converge to 48.8239 and 0.0070. So of course, this is the case where we have not added any lambda at all. Now we can try adding some lambda to it. Let's add a really small lambda, 10 power minus 7. And you can see that this still converges within 5 iterations. Levenberg-Marquardt is better behaved. That is, it damps lesser than Tikhonov actually. As you get closer and closer to the answer, you get better and better. There is a way of actually changing lambda, scheduling lambda. As I told you briefly within our class, you can actually change the lambda value as you go through the iterations, but we are not going to do all such fancy things. We are just going to stick with the basic algorithm just so that you get an idea. After all, this is a methods course rather than a full-scale application to any practical problem. So this is just primarily an intention is to for you to understand methods. So okay, so now in the 5th iteration, you see this 48.8239 again. We can play with lambda. I can make it a little bit larger. So it just makes it a little bit slower. Okay, so you have damped more, it makes it slower. If I make it really large, like lambda equal to 1, it doesn't converge, or at least it takes longer, much like Tikhonov. Okay, now we can try the case with the farther away lambda or farther away initial condition. You will remember that it took around 9 iterations to get there, and now we can try it with damping. Okay, so we can try it with the Levenberg-Marquardt algorithm, where I changed the lambda to 1 e to the power minus 7. I should put 1 dot 10 power minus 7. So we are still getting 9 iterations here too. If I make it 10 to the power minus 4, you see 7 iterations, which is a little bit faster than what we had earlier. We had 9 iterations. So Levenberg-Marquardt actually offered us an acceleration over simple Gauss-Newton with this initial condition. I can try a little bit larger lambda. And here you see again 7 iterations. Maybe it's converging a little bit faster. You can also see that the value of B has very quickly converged to 0.0070, which it did not for Tikhonov or for Gauss-Newton. So Levenberg-Marquardt seems to have certain advantages for this example. Again, I would warn you from making a generalization from here. Generally, it is true that Levenberg-Marquardt is better than Gauss-Newton, and Tikhonov is also better than pure Gauss-Newton. You have to play lesser with lambda and Levenberg-Marquardt in order to get good performance. And you will have to play a little bit more with the Tikhonov lambda in order to get good performance. Overall, in general, in all practical problems, it's best to use Levenberg-Marquardt. I'll show you later on when we come to the machine learning portions that when we use Levenberg-Marquardt, in fact, MATLAB uses Levenberg-Marquardt by default. And of course, it has a sophisticated internal scheduling routine that makes convergence really fast on fairly complex problems. So we will see that later on in the course. So that's it for this video. We saw a couple of examples of Tikhonov as well as Levenberg-Marquardt applied to the standard problem that we used in the last week. The theory you had seen earlier. So that's it for this video. Thank you.